Hello everyone. In this video I will be telling you about the thermodynamic probability of Maxwell-Boltzmann statistic. So in order to start with our derivation, I would like to start with that here we are assuming a simple box containing a large number of particles inside it, and it is quite obvious to us that at a particular temperature all the particles will not have the same amount of energy with it. So the amount of energy possessed by a certain group of particles will be different as compared to the other group of particles inside the box itself. So here if we take a look at a graph that we can draw of between the number of particles in the box, and I am writing it as energy Ne, that is number of particles possessing certain amount of energy, and in the x-axis I am drawing the energy. So normally we would have seen a graph like this, exponentially decreasing graph. So this is explaining that this number of particles having an energy corresponding to this, say it to be E1, and then these number of particles is corresponding to energy E2. So like this. So all the particles inside the box will have different amount of energies with it, and this is what I have drawn here in order to explain that. This is I had drawn different levels of the energies, and different particles inside the box will have these type of energies like E1, E2 and dot dot up to En. These are the different levels of energies, and and here I am assuming that the total number of particles inside the box to be n, capital N, and from this n, say n1 number of particles have energy E1, n2 number of particles say have energy E2, and similarly nth number of particles will have energy En. So in order to start with the derivation, here we are basically aiming to find the total number of probability of the total number of particles inside the box. So here first what we have to do is that we have to choose n1 number of particles from the n possessing the energy E1. We can do it simply by combination. From the probability chapter we know that selecting n1 particles from the n can be written as NCN1, which is equals to n factorial by small n1 factorial into n times n minus n1 factorial. This we can write from the simple combination formula, that is NCR. So after this we can also write that after we have selected n1 number of particles from the total n particles, we are left with n minus n1 particles. So from this number of the particles, we need to choose n2 particles possessing the energy E2. We can do it like n minus n1 C n2, which can be written as n minus n1 factorial divided by n2 factorial into capital N minus n1 minus n2 factorial. So similarly we can also write it for further particles, but the overall number of ways in which we can select n1, n2, n3 dot dot up to nn can be written as, say we are denoting it with W, we can be written as nc n1 times n minus n1 c n2 times n minus n1 minus n2 times n3, and this will continue up to the last. So here if we take a look, if we expand this, we will get W equals to n factorial by n1 factorial into n minus n1 factorial. Then again in multiplication we have n minus n1 factorial by n2 factorial into n minus n1 minus n2 factorial, and this will actually continue. Here I just want to make you see that these terms will get cancelled up till the last. So the final thing that we will be left out with will be W is equals to n factorial divided by n1 factorial into n2 factorial into n3 factorial, and so on. So here it can be written as n factorial divided by multiplication sum, that we are adding the total number of, this is ni factorial, and here I is varying from 1 to n. So this is the expression that we can write for the number, the ways in which we can distribute the different number of particles in a box. So this is one part of our proof. Now it is obvious that the different energy levels that we had in our starting of the while distributing the particles. So here suppose this was the our energy levels E1, E2 and so on up to En. So here this E1, suppose this was E1 and this was E2 and this was En. So further there will be distribution of the particles in a single energy state also, that is there will be degenerate energy levels inside a particular energy level itself. We had heard it about in our complex chapter, that is complex coordination compound in chemistry, that the different levels of energies are further divided in a particular energy level. We call it as degenerate level. Similarly here also a particular energy level can have different degenerate levels inside it, and we need to also take into consideration those things while distributing our particles inside a particular energy level. So if we take that thing into consideration also, then we have to distribute the particles. Suppose here in E1 we had n1 number of particles inside it, we need to take into consideration the combinations of these n1 number of particles inside these degenerate levels also. So if we take a simpler case, suppose here I am magnifying the first energy level. Suppose this is our energy level E1 and it has been divided into 4 parts, 1, 2, 3, 4. And now here if we come up with a single particle from the box possessing energy E1, this single particle can have 4 probabilities to get divided into this single energy state E1. So it can either go in the first degenerate level, either in the second, third and fourth, anything. So this particular particle can be placed inside this energy level in 4 different ways. Now if we come up with another particle, like say this is particle number 2, this is particle number 1. So now this particle 2 will also have 4 probabilities to get distributed inside this energy level E1. So it can be distributed inside it also in 4 ways. So overall these 2 particles can be distributed inside this in 4 into 4, that is in 16 different ways. That is, if we elaborate it, if we define the degenerate levels with Gi, so Gi raised to the power n, where n is the number of the particles that we are taking into consideration to be divided in a particular energy state. So here one more thing that I want to specify, that as we are dealing with the particles obeying the Maxwell-Boltzmann statistic, so these particles has the speciality that they infinite number of particles can be placed in a particular degenerate state. Therefore because of that reason we are not taking into consideration that only why there is no restriction, actually there is no restriction to distribute the particles in a particular degenerate level in an energy state. So that's why we are simply making the things here quite easy. So if we take into consideration all the degenerate levels of all the energy levels E1, E2 up to En, so let's say I am denoting it with the P. So P can be written as Gi or G1 raised to the power n1 into G2 raised to the power n2. So now this will continue up to Gn up to nth particle. So if I write this in a compact form, this can be written as multiplication summation of Gi raised to the power ni, where I is varying from 1 to n. This is our second part that we are looking at. This is our P and this is our second part of our derivation. So till now the results that we have got after doing certain calculation, this is the part 1 that we have got and this is the part 2 that we have got. So combining these two things, we will get the thermodynamic probability of Maxwell statistic. We are denoting it by this symbol. MB denotes Maxwell-Boltzmann statistic. This can be written as W times P. So if we write it in a further manner, we will arrive at n factorial divided by multiplication summation of from I equals to 1 to n I factorial multiplied times pi, or multiplication summation from I 1 to n gi raised to the power ni. So this is the thing, or if I write in a further by simplifying it or in a compact way, so our final result is n factorial divided by I equals to 1 to n I whole factorial times pi from I equals to 1 to n gi raised to the power n I. So this is our final result of thermodynamic probability of the different number of particles that can be especially Maxwell-Boltzmann particles. So there are different categories of particles also. We are here particularly dealing with the particles of Maxwell-Boltzmann, and this is the probability or thermodynamic probability of those Maxwell-Boltzmann particles. I hope that you all understood it.